Okay, still on. Let's see. Okay, let's start. Hello, welcome everybody. Sorry, I still try to bring the microphone online, but it's still a problem. Therefore, for the online participants, there's just audio from this small video camera, and which is always a little bit difficult to grasp afterwards because it's not well recorded, and this microphone is unfortunately not correctly connected to the entire infrastructure. Why, I don't know. I try to find out whether there is a small mute button somewhere inside, but I can't enter the entire technical equipment here. Okay, so let's start with our lecture, Physical and Database Modeling. Hopefully, last week there was no confusion with regard to our lecture. Hopefully, there was no indication that there is no lecture, because as you might have seen. And today we continue with our considerations of general physical modeling. Particularly, our aim is to understand the basic and the general principles of physical models. And we started last time of finding out similarity between the hydraulic world and the electrical energy world, and we find the very same for pipes. So on the left hand side, if you have a very simple pipe and there's water flows through, then you will find the same situation in electrical engineering. There is some similarity if you define the volume flow as a correspondence to the current in electrical engineering, and the pressure as a correspondence to the voltage. And so the voltage drop here is U, and you might have a pressure drop P1, P2 minus P1, then you have the very same situation. And the interesting fact is that such a pipe acts as an energy storage and behaves similar like inductance. And we can use this information, for example, storing energy in district heating networks. This is an example I mentioned last time. So we did it in a huge city in the northern part of Germany, and we can save millions of euros by just reducing the fluctuations in the network by storing energy in the district heating network, which is existing. Not every city has a district heating network, but there was was possible, and from my perspective, it's a good idea to use the existing infrastructure by a short-term storage. And the interesting part is for reducing fluctuation, it's sufficient. For long-term, it's not sufficient, as you know. So inductance cannot store energy for a long time, so there you need something else, which might be capacitor. So, well, a similar applies for the dissipative elements. We have the resistor in electrical engineering, and the general notation is similar. We use the electrical engineering formalism to depict resistors. And on the right-hand side, you see the bond graph notation. At that point, it seems a little bit strange because you write down R double dots R, which means here the second R represents the true value. So, for example, 50 ohms or 500 kilo ohms. So it's R is indicating that it's a resistor. If you have the capacitor, then the C is indicated, and behind the double dots you find the true value, and might be also a variable which stores the true value. So it's perhaps better to write down R1 as a possibility to indicate that that's just the value. Usually we indicate the corresponding variables. You know, we already have two, some sort of a cross metered variable like the voltage, the pressure, or velocity in the mechanical domain, and a flow variable in electrical engineering, current, in hydraulics, volume flow, in mechanical engineering, force. So we have the same situation, and there is a correspondence. We know the Ohmic law, which is representing a linear relation, but sometimes, in particular in other domains, we have nonlinear relations, which make the situation quite more difficult than we know from electrical engineering. If you look, for example, in hydraulic networks, we have nonlinear relations, or in gas networks, we have nonlinear relations, which we have to consider that. Here's an example. It's not necessary to know this. This is depending on the specific domain, and you have to jump into. You should understand the basic principles. You should look for such a relation between a flow and pressure correspondence, which is given here. E is equal to something nonlinear, depending on the flow, which is the typical relation. And this is the case for pressure drop in some conditions. We find something like this. It's here you see the specific behavior. As in electrical engineering, we again find something like this. Of course, there's a geometric perspective on it. So, as you know, the resistance of a simple wire depends on its length, its diameters, and of course the material constant. Copper is different to solid wood or so, and here is similar. You find geometric constants, obviously not similar, but because it's a different physical object, and there's something corresponding to the viscosity in liquids. So, of course, if you have honey, it's different to water. So, as you see here, same situation for an electric resistor. Okay. Well, if we glue everything together, and here you find it tabulated, you find out there is always a generalized flow, generalized effort, and in electrical engineering it's depicted here. In mechanical, in translational engineering, you find force and velocity. And as I mentioned, might flip this these two definitions. It's not precisely defined, but please, if you use one definition saying, well, force corresponds to flow, please stay on this. If you make an interchange of these variables through your calculations, you get really lost in the following calculations. So be careful with that. So always stay at the same definition. And just again, as a hint, if you read books, they always define it differently. Sorry for that. Well, researchers have not, find a way to define it consistently, always the same way. Sorry. Hydraulic as even and climatic. I put it here already in a delta notation because very often climatics depend on some sort of linearizations, and you can do it in that way. So again, the generalized components. This is a notation which just says, okay, if you want to represent a physical object, you can represent it as an electrical equivalent circuit, you can represent it as a bond graph, or you can do anything else with similar features. But what you know is you always have a capacitor, inductor, and resistor. It's always the case in these domains. So if you go down in the question, what governs a so-called lumped parameter system, then we end up on saying, okay, we have two types of storages, one dissipative element and that's it. Basically, if we look just at the one-port elements, one port means one power port. If we look at two ports later on, then we have much more, but if we break it down, what governs nature, then we end up with this. That's it. You don't need more. If you don't find everything, then you can ask for it. Then you have a problem. Usually there is a second, for example, storage. So same for electrical equivalent circuits in the mechanical domain, here translational. So capacitor corresponds to a mass, a movement of the mass, so it's kinetic energy which is stored there. A spring might be is represented by means of an inductor and with a specific inductance, and the inductance is given by 1 over the spring constant. And last but not least, everybody knows something like a damper which you have in cars, or even the closing mechanism of these doors over there. And there's some sort of dampers which operates at this way with compressed fluids, and you have the representation. And now you see a good picture of what we have today. You usually have the possibility to use the equivalent circuit. The bond graph representation, or on the left hand, you use that what we know from the domain. If you're a mechanical engineer, well, you're not so happy with the middle part here. So the column in the middle, well, mechanical engineers do not like to represent everything as electrical engineers and vice versa. So therefore, the interesting fact is, if there is such a full correspondence between the two, then why not using the things we know from our domain? That's interesting. During my time, when computer power was not certain, when I studied these things first, I was forced to learn everything to translate everything into the right hand side. So to translate a mechanical object into a bond graph also. And if you look at the bond graph and you're in the training, it always looks a little bit crazy. You will see some examples later on. Today, and we will look at examples today in our time, why computers do that, because it's just a different picture. And the most, or the best, no, I tell the story later on. So same for the mechanical engineering and rotational situation, we have this correspondence. And what I want to say is, well, there exists such a general language on the right-hand side. So you can replace it, but you are not forced to do it. And if there's such an existence of such a general language, then, well, I understand the basic principles, and we can look at these principles later on. And here is my example. On the on the right-hand side, you see how we represent a system, a string damper system, with a network approach. What you see here is a string damper system, some mass, which is indicated by means of a mass block. Here's the damper, there's the spring. There's something, and when I want to write it down as pictogram in PowerPoint engineering way, so I'm sorry, and I would write down something like this. I have a mass, I have a spring, and a damper. That's it. That would be my picture. If you look here, just in the middle, you find exactly the same. Why is so wonderful? Because this thing here is completely represented by a so-called non-causal version of the system definition, the system mathematics, how it behaves. Because in the string, in the damper, in the mass, we find the government placements. We are able to solve this. We have to look what such a computer has to solve finally. But the interesting fact is, please believe me, there is a computer program which starts with this pictogram and solves it in simulation. Interesting. So, well, you take your object, your physical object, you can represent it as it is. And physical relation, you can also write down the bar graph, but you can use it in your pictograms you like to use. And then there's a solver which simulates the system. Well, we do not need MATLAB, we do not need simulation, sir. No, it's not necessary. For simulation, it's fully sufficient to represent it in this way. By the way, this is not all. In the encircled area, we find the system. On the right-hand side, you need something which indicates the force, because I forgot something. There's perhaps, sometimes I write something down like this. There's a certain force acting on the system, which is indicated over there. And of course, if you want to do measurements, you have influence on the system as well. If you do measurements in an electrical circuit, for example, if you want to do power measurements, you insert something like a resistor, and therefore the measurement is also included. So basically, to make it in different colors, here you find F, which is, oops, sorry, over there. F, and over here in green, perhaps, this is a motion sensor which just captures the motion of the speed of the mouse. And with that, you can finally add it to a scope which, well, depicts the movement, like the velocity. And the wonderful thing is, well, you do not need equations at that point. You do not need anything else. It's very simple. You state the domain, and that's it. Perfect. So for simulation purposes, wonderful situation. And well, Mr. Kiesler will simulate this with you in the first exercise lecture, and show you that later on. Well, what you know is the thing on the left-hand side. this is the string data system in Simulink. It's the very same thing. The scope on the left-hand side depicts the same version like the scope on the right-hand side. Well, when we produce a Simulink block diagram, what is different? Question for you. What do you think?
We have to know the entire differential equation and the different concepts.
And we make it explicit in particular form, so we say that there is x dot is equal to something, so we can write down the equation. What is the step from the right hand side to the left hand side?
Probably sort of state model.
Exactly. So the fundamental question is, in which way does SimScape simulate this picture? It's just a picture. And we should look what step are we doing if we go to the left side. Okay. But and this is something I want to show Bruce. To get a little bit forward to show you that, because oops, something we want to treat later on. So if we look at the equivalent circuit model, like in electrical engineering, if you want to do and write down the equations, what you did in the first semester in the bachelor, did you do? What was the first thing? Was circuit analysis, it was called. So like loop analysis, nodal analysis, writing down trivial laws, etc. And at the very end, you end up with a set of algebraic equations, right? And differential equations like L times the di dt is equal to and something. So you have a set of equations which just have an algebraic relation, and the second set where we have the differential equations. Very often on the left-hand side is some sort of derivatives of some of the values which are connected by algebraic relations. So if I and or if you think of this was always the problem, it's not always just an algebraic relation and a differential equation. Sometimes we have also integrals, right? So integrate the value x times c gives you also something like that. All these together looks like this. You get some sort of a so-called integral differential algebraic equation. This is the very starting point. So the mathematical object of such a equivalent circuit bond graph is just a differential algebraic integral equation. It's followable and unfollowable. And if I write it down in the most general form, it looks like this. Formulates a derivative of some of the variables here, some integrations, and some equations are directly given. So on the left-hand side is equal to zero. So you have a set of integral equations, some differential equations, some algebraic relations. So all grouped together in one super vector. What did you do in linear electric network analysis to find out the differential equations? What's that to do? We do the very same thing. Yeah. So if I have integrals, what can I do to come to differential equations? It is that simple. What do you think? Yeah, integral of something is equal to a volume of t. How do I get rid of the integral? Yes.
differentiate one.
Yeah, exactly. Substantially often differentiate both sides of the equation, and you get at some point just differential equation. So getting rid of the differential equation seems simple, but for avoiding the algebraic relations, it's not that easy. What did you do in linear electrical networks? Because they're typically Kirchhoff's laws bring some algebraic relation between some of the values into the equation. Okay. Any other? What did you do?
Just some kind of Laplace transform and.
Yeah, that's solving that with the Laplace transform, but just how to handle the algebraic relations was always a tedious task, and we do mistakes in that. So I do. You solve all the algebraic relations, right? So you sit in the exam, set in the exam, and solve the algebraic relations for some of the values to reduce the number of variables. So it's more or less like this. In the most general form in linear case, it looks like this. You get this object here can always be transformed in some sort of a matrix E times x dot is equal to x plus BU. It's similar to what you know perhaps from linear multivariate control from Mr. Kubi already, but there's something mysterious about it because here E is given, and E has perhaps some entries which are completely zero. And then you have 0 is equal to some linear equation, some linear relation. So represents a linear equation. And then we have the most general object. So what I wanted to show is the solver is in Simscape, and this brings me back to when I tell you the story later on with this. Simscape is capable to solve these kind of so-called differential algebraic equations. It's like a specific Euler form, what we already know. So a Euler discretization or Tusson discretization or Wunsch-Hütter discretization, you know already. From numerics, you enter this, and with that, you are able to solve differential equations. And similar to also this for differential algebraic equations. What is so specific about this? These differential algebraic equations are solved, and that way that the solver does a step for you. I go back in the pictogram, which is here, hopefully. Here it comes. Well, here, if we look at this network, it's just a linear network. You solve it as having a differential algebraic equation. If you want to go for a classical solver, you know, like Euler discretization or Tusson or a Wunsch-Hütter, well, you have to make it explicit. So something like x dot is equal to, and then you can apply the Euler discretization, and then you end up with something similar can do it for you. If you're on the right-hand side, the solver does this equation solving for you. And now, you might ask, why are we using Simulink if the right-hand side is existing? It's so much easier. If there is a solver who does the job for me, why should I use Simulink? Doesn't make sense. Because there's a computer, if not wrongly programmed, then, well, it does not make mistakes. I make mistakes by hand calculations because, or typing this into a symbolic solver, to end up with the left-hand side, sometimes, well, error prone. Why not? Well, putting this on the side of the computer, and yeah, it's a question for you. What do you think? What is the advantage? On the other hand, we can tell you from practical experience, if you look in companies, what tools they are using in terms of in the control engineering department or in the design department, for example, for controllers or stuff, automation technology, they use similar method. They do not use the right hand side usually. What do you think? Why it's the case? Why do we find still that hand side? Because right seems to be easier for us as engineers. That's it. And if you learn something about differential algebraic equations, control engineering, it exists, but it's hard. So it's not the standard way. The standard way starts with the classical equation, differential equation, so the left hand side. And there exist a bunch of tools which are ready to use. And therefore, if I'm just seeking, or if I'm looking for design, looking for controller design, I'm much more on the left hand side because I needed explicit differential equations for my design class. Remember our control engineering class in the bachelor. We start with the differential equation, make a linearization, and then we can use root letters or Bode plots or loop shaping or whatever. But we start with differential equations. Right hand side, you do not see anything. If you're just interested in simulation, right hand side is wonderful. Because we are not dealing with differential equations, we're just wanting to know what are the results, so v and x in our case here. So it's much more favorable to use that. Just to give you an impression, just a practical example where we use Bode in the times when the first type of cars were invented. So Toyota was one of the first popping up with the Toyota price, I think. It's a hybrid car. Everybody thought, hey, this is the new world. And the traditional car manufacturers here in Germany, field of Toyota states and said, okay, we need to build hybrid cars. Was a substantial push into that direction. And then the question appeared, and this brought up a couple of questions. The question appeared, what would we do? What kind of hybrid strategy should we use? You should know a hybrid car has a combustion engine and an electrical drive, and you can touch the electrical drive very differently to the combustion engine. You can make a serial connection, like in the train. You have a combustion engine which drives the battery, it generates current or power, electrical power. This electrical power is then used for a electrical drive, serial connection. You can attach wires on here, the hybrids, the electrical machine to the combustion engine in parallel. So you have a so-called power split. You add power from the combustion engine as well as from the electrical drive. You can just add the force. We can put it at the rear wheels. We can put it at the front wheels. In addition to that, well, you get the question of recuperation of energy. What we know very well, but at that time I was responsible for the braking department, therefore I was quite heavily influenced by that. At that time, we had just no brake-by-wire system. Why do we need a brake-by-wire system? You have two classical cars. You press the pedal, then you have a hydraulic loop, and you end up at brake discs. No recuperation anywhere. If you want to just recuperate something, then the electrical machine brakes for you. And if the driver presses the pedal, the machine should brake. but you don't need additional hydraulic braking, so you have to reduce the hydraulic braking in correspondence to the electrical braking, which makes some sort of electrical interference with that. You need a complete new braking system, which is could be phase safety, etc. And then the question is, how do we do that? At that point, it was quite difficult because guys at that time said, well, it's important for safety reasons to have always a hydraulic connection or two, better to say, parts, two different and separated hydraulic connections. And then the question appears, how much is it allowed to brake just at the rear wheels, because this defines the recuperation, the number of the amount of kilowatt hours that can be recuperated. So a couple of questions, and the interesting fact is these questions span over the entire company, from the braking department, over the combustion engine department, over the housing department, whatever. Everything was influenced by that, and every domain was influenced by that. And at that time, we have a simple question. So management question is, just to make an impression, Mr. Hohmann, what's the difference between your strategy A in braking system and B in terms of how much fuel is saved or reduced? How much is the fuel consumption reduced? Okay. Well, I have no answer. I can say, well, this is cheaper, this is more expensive, and this is more difficult to maintain. And well, here we have knowledge, there we don't have knowledge in our department. This is completely new, this is old. Yeah, but this is not the customer value. The customer value is how much money he saves if he buys this or that car. We were not able to answer that at that time because we need some sort of fully functional simulation of the car. Right? From the combustion engine over the braking, recuperation, electric drive, some sort of batteries. Well, it's not connected because the driving dynamics guys were working in simulating. The combustion engine guys were working in more finite elements methods and rules of thumbs. And the electrical engineering guys also rules of thumbs and also some sort of simple simulations for the electronics. So it wasn't possible to answer that question. And then you can do two different things. One thing is you couple all these different types of simulators. So simulate some sort of simpler for the high power electronics and so on. So a couple of simulators which have to be glued together. So you have to produce interfaces, one way of doing it. A lot of work, you have to do it on your own because you're the only company who uses this combination of tools. Or you transfer everything in the same language. And this was done at BMW at that time. So on the right hand side, this was the way of doing it. Representing this entire car fuel consumption story into some sort of SimScape at that time, Daimler, different tool, so it exists from different companies. So wonderful, isn't it? And at the very end, simulation was possible. So again, it was possible to simulate how much fuel is reduced in terms of reduce this or that hybrid strategy. But it's not sufficient for design. Okay. And now the best business case ever, since you know the mechanical engineer uses this pictogram and this damper, this spring. The electrical engineers use their symbols. The hydraulic engineers use the piping schemes. And the software Daimler, well, is now not, you are not forced to program it in one graph notation. No, you put it there in the notation you know from the domain. This is wonderful because they sell the mechanics toolbox and the hydraulics toolbox and the pneumatics toolbox and the air conditioning toolbox and so on and so on. And you know, principles are the same. So behind the story, behind the scenes, we have always the same thing. The only thing which changes is the picogram in front of it. And if you switch from now, it's included, but at that time you have to pay for the mechanical part and the electrical part. Always some one license, 20,000 euros. This is a business case, isn't it? Just a picogram. Yeah. Well, you can check this. It's quite easy. Today, MATLAB, so MathWorks at that time never saw that's really a big competitor because it's a completely different story to the story. And they really lately invented something similar. It's bought a company called SimScape, which is now included in MATLAB. It's also in the in MATLAB, the student version you have access to. So please feel free, type in SimScape, the window pops up, and then you can play around. It's quite intuitive. That's what I want to say. Please do it. Simulate whatever you want. So even I did it with my garden watering system for watering my lawn, because there you have the question, how much pressure do I need that the latest sprinkler is still moving up, and I did it in that way. So it was quite easy. I'm not a fully hydraulics engineer, so but for me I was happy to see, okay, with this diameter of pipes, and so for me it was helpful to design my watering system. So if you have any other questions in that direction, so please feel free. All robots. Now the interesting second fact is, now I want to ask the following question: what do you do if you build microcontrollers? May I ask? Am I in the right lecture here? Microcontrollers. What is the story of building these super huge microcontrollers with their design tools? It's just a transistor, resistor, capacitor, inductance in such microcontrollers. What's the basic idea of designing super huge frameworks of new microcontrollers, for example? It's the nesting of information by object-oriented programming, right? Isn't it? So if you look at the tools, you reuse modules, you reuse modules of modules, and then you put a frame on it, around it, and say, okay, I use this module, and the additional, I have a fully, calculation network for addition and subtraction, a buffer. It's completely a flip-flop built by flip-flops, and you put it all together. It becomes bigger and bigger and bigger and bigger. And the wonderful thing with the right side is possible either. So you can glue together simple things, make so-called components out of it, and can reuse it because you have a physical interconnection. There is no signal flow like on the left-hand side. We transport information, because if you have a completely new electrical, for example, if you have a completely new electrical network, for example, then you have to recalculate all the equations, and you get a completely different left-hand side symbol like dot diagram. The right-hand side stays the same. You can reuse the information. And if you're interested in how should I organize such information, how it's calculated in terms of how it's architecturally integrated in such a story, how can I build bigger systems by means of object-oriented or methods of object orientation, then please, here's a second lecture out of our institute on cyber-physical protection systems and digital twin engineering. And in both lectures, you find something about the architectures of such things. So here are the fundamentals. You know now why Mike Bart is saying, hey, it's the very same always. Please reuse it, and then you can build robots and so on. Last story about this. The first step towards this in the 1980s was done by DLR, the German aerospace center, for simulating huge robotic arms on the space shuttle for manipulating from mechatronics parts. It's a mechatronic system, and at that time was not possible. And the professor at that time there thought, hey, it must be easier. I want to reuse these things, etc. So wonderful thing. So that's about the story here. So what we can do and say, if we look at the mass spring damper system, the causal modeling or the non-causal modeling, we put here a plus is perhaps no explicit differential equations. A plus is perhaps also reuse of models. But there are some consequences. If the computer does the calculation for you for solving for the algebraic equation, the simulation time is usually longer than when you did it by your hand, right? So only in simple cases, it's not the case. So usually we can say more complex simulation. So simulation time is higher. And the second drawback is not ready for design, what you also mentioned. So what I mean, control design, some sort of design. So in such a simulation design iterative procedure, it works. Okay, you can adjust the parameter and you can look what the simulation does, and then you can adjust the parameter, look what the simulation does. It's work, of course. But for calculated designs, like in control engineering, with calculation, it's not possible. So on the other hand, we have here as an advantage explicit differential equations. This is wonderful. Sometimes. So controller design. Easily accessible. Okay, but there's a difficulty in reusing models. So, well, if you force simulate in a certain way, it's also possible, but it's not that easy. In particular, some sort of, well, how mathematics becomes so popular, you reuse everything. You reuse the things from the very simple building blocks. Nobody programs a menu for Windows, as I said. You reuse the menu things somebody did, well, years ago. Software becomes bigger and bigger. So we manage complexity by information hiding by reusing objects, for example, and that's popular for the ACOSM one. So that might be possible. So if you have explicit access to the differential equations, and if you implement in the differential equations your controller, you can also automatically generate programs from all of it. So some sort of automatic code generation works easier on the left-hand side than on the right-hand side. That's why, well, very often if you want to have access to automatic C coding, left-hand side might be easier. Yes, that's okay. Here is it. Some word points listed, and that's it. I think that's important to know. There is not one way of doing simulation. There's not one way of representing a system. And in particular, if you want to understand the principles, if you want to understand the entire physical behavior, the causal modeling is more appropriate, and please use this. We as control engineers very often, and I started with this question at the very beginning of this lecture series, I said, well, usually you have two questions. You have the design question, well, it's more similar, and you have the, well, test validation question with more complex models, because for representing the physical behavior, you want to be more precise, less abstract, and then you have a more complex model for simulation, usually, the second model for design purposes. It's quite typical. You have at least two models in such things. And if you're interested how to organize all these models, again, the two other lectures are highly recommended for understanding this. Please feel free to look up. Okay. The next slides are just for your convenience. If you're looking for the respective systems, then of course energy plays an important role, and then we find some sort of energy behaviors, and as you see, we have for linear systems, we deduced this last time already, that the co-energy and energy are the same, and for kinetic and potential energy, or for accumulated and flow energy or accumulated force potential energy, we find these. And this is more for your level usage, right? You find the very same for hydraulics, find the very same, and that's so. Okay. I just wanted to highlight, okay, it's tabulated, it's nothing you should know, in particular for our examples during the exercise lecture, please refer to that. During the exam, so the oral exam, I use very typical, simple equations. If you don't have the energy, well, please ask. Not a problem. My intention is not to explicitly test whether you're a super mechanical engineer, energy guy, or women. I'm much more interested in whether you understand the basic principles, how everything is glued together. So displacement so much role in things. Okay. Well, up to now, there Great. What I mean is, well, now we have heard something about the, I'll say, one-port elements. Of course, we know with one-ports we can solve some problems, but not everything. So simple networks, simple things we can understand. But there are two questions open. One is, well, what's about with multi-port elements? Well, I should reduce the question, what's about two-port elements, because they are quite difficult. But what's about that? And we discuss this in a second. And second, well, is there a fundamental procedure how to glue these elements together? How do we do that? Is there also a principle behind it? So what you learned in electrical network engineering in the very first semester, is this appropriate also for other domains? Good news, yes. Bad news, for bond graphs, you have to learn it a little bit. For mechanical, if you start with the mechanical object, transferring this into electrical engineering network, this has to be trained a little bit. But it's also helpful because if you look at it from electrical engineering knowledge onto a mechanical object, you see also something which it might be of interest. So this is something we have to learn. And the last thing I want to mention is if there is so much structure behind it, then we should understand where state-based models come from. We should understand what is the state. So I can ask you, what if you remember, you should have heard this in signature systems, multivariable control systems. Yeah, what do you remember? And also control engineering. We talked a little bit about the state. What is the state? Do you remember that? Or first question, you heard something about multivariable control or this lecture already? Yes, we did, and I remember we did it already. But what does it tell you about the state? What is the state? Some sort of energy. He always says it. Yeah, something else.
In the state, it's just specific state systems in so specific values of all the different of the system. And it's often you can use energy related state because it's easy to describe system.
Yes, all right. But what is it physically? I found it, when I was a student, I read the first definition of a state in Föllinger's book. And he wrote the following sentence, well, more or less in that way. Said, a state is something with which I can predict the state in the future. And it's the full description of the system. And I thought, yes, perfect. This helps me to understand what the state is. Later, somebody told me, my predecessor, who said, well, a state is somehow related to the integrators in a system. Also nice. Second question, second point. I also did not understand what it is. Last definition or last point was, well, in my own lecture on control engineering in the bachelor, I say, well, control engineering is nice because it applies to everything. And nobody asks why. I always say, hey, you can use it for robotics, you can use it for mechanics, you can use it for flying, and so. So control engineering is for almost everything. That's the nice part of the story. But I never proved it. And the question is, and we should answer it, yes, why? And the answer is somehow given already here, if a system is somehow always represented by similar elements, then we should be able to capture these general principles in the same, well, with the same formulas, isn't it? So that's part of the answer, and we have to answer this in that direction. And if this is the case, then there should be principles behind it, and therefore, well, we can do robotics engineering, control engineering, as well as airplane flying or drone flying or whatever, as well as automatic driving, and with the same structures, by the way. And that's the main point. But before we can do this, we have to learn a little bit about the so-called two-pole elements, because they are very important in particular in coupling different domains. And we can say, okay, there's some sort of subsystem 1 and some sort of subsystem 2, all glued together with power ports or bonds. And in between the two, there's a transducer, something which transduces, well, or couples one subsystem with another. This can happen in the same domain, but also in a different, from one domain to another, from the mechanical domain to the electrical, vice versa, from the mechanical to the hydraulic domain. We should answer how this works. And last but not least, the transducers couplers can either be storage big as well as energy storing, due to the working principle. That's important. And we should look at the different working principles. For the mechatronics engineers in the room, we learned something about the storing elements as well, because energy storing elements which are also important for some reason. So if we do this overall picture, then we have so-called single domain coupling elements, then we have cross domain coupling elements. They might be energy storing, power conserving. Then energy storing may have a capacitive principle and inductive principle. Power conserving might be an ideal transformer, ideal gyrator. We learn a little bit about that. And last but not least, I should add, there's a last principle which transduces also, which behaves a little bit different. It's the piezoelectric. Oops. Which is also existing here. So we have three working principles. We just look at the two highlighted here on the slide, but but basically there's three. Okay, so we start first with the power conserving. They are the simplest forms of transforming energy, and you find these elements already. So the basic idea is idealized transducers. That's important. So please here refer to idealized transducers. It's really important. So the entire power which comes in goes out. That's the working principle. And there is no dissipation, there is no storage, nothing. Or better to say, we can attach dissipative as well as storage elements to the transducer idealized working principle on the left or right hand side of the transducer itself. But it's not completely part of the working principle of the transducer. This is something you have to understand, and you will see why if we see both worlds. And this does not mean that there are no storage elements at all, but they can be completely separated from the transducer working principle. That's the basic idea, and we will see that's something you already know, but without knowing that's the general principle behind. And I want to start with introducing a transformer, which you already know from electrical engineering. And the working principle is given here in general as follows. The effort variables are coupled. So the effort variable on the left-hand side, port 1, is coupled to the effort variable on port 2 by means of an alpha. So it's just a linear relation. Alpha times AE2 gives E1. And the same happens with the F values, but reciprocally in a reciprocal way. So F1 is equal to 1 over alpha times F2, and that's it. And quite simple. In bond graph notation, you find something like this. You have a bond in and a bond out, and transformer as a symbol for indicating, hey, it's a transformer, and the transforming value alpha is given there. So I give you a simple example. If it's called transformer, then hopefully the electrical transformer is a transformer in this definition. And the wonderful answer is yes. In general, yes. Sometimes, let's see. I want to show you this. Okay, so a little strange definition of the U values and current values for an idealized transformer, which is given over here, electric. Let's have a look at the flux linkage. You have the self-inductance and the coupling inductance, what you know. Be aware of the definition of the voltages here and there, which changes the sign of the law of induction, no? Which gives this equation, and we know that the induced voltage U1 is the time derivative of the flux linkage psi 1. And the same applies to psi 2, which is quite clear. We have the self-inductance of the windings, and then we have the influence of the other side, which is usually defined by the coupling into inductance M12. Very simple definition. Now I want to show you some nice behavior. Sometimes, well, usually I should say. Very often in practice, we can say, hey, M12 and M21 are equal, and we define it as M. And very often M itself is designed in that way that it corresponds to L11 and L22 and the square root of it, which simplifies the situation a little bit. So we get psi 2 is equal to the square root of L22 divided by L11 times psi 1. And if I do the derivative of both sides, psi 2 is equal to the square root of L22 L11 psi 1 dot. And obviously this is U2 and this is U1. So what we see here, obviously, the effort, so we define the transformer in that way. So let's have a look again. E1 is alpha times E2. E corresponds to the effort variable, so in our case the voltage, and we can write it down as alpha being the square root of L11 divided by L22. And that's it. So here it applies. That's what you know. This is the working principle of the transformer, isn't it? So the voltages are transformed that way. Now let's have a look whether it applies also for the currents. And therefore, I need the next slide, hopefully. Yes, I just wait until
You wrote, took your notes. Okay, so next, let's write down I2 is the negative of, just I inserted the equations I did. Obviously, there's a problem. There is no correspondence between I2 and I1 in a simple way, because here this nice guy enters the problem. If assume this is not present, then we have the relation I2 is equal to 1 over alpha times I1. So what we know already, but it's not the case. Now I ask you a question, under which condition this equation, this part of the equation vanishes, becomes zero? First a mathematical answer and then please a physical answer. Yeah, there. First the mathematical answer, because it might be easy. Which condition is the first sum equal or close to zero? If what do we have to assume? Yes, please.
Maybe it's going to be close to infinity, or
If L11 is close to infinity or L22 is close to infinity,
close to zero.
then it goes to zero. So L11 is the self-inductance of the inwinding, L22 the self-inductance of the outwinding. What physically do we have to do that the self-inductance becomes infinitely large?
Number of windings.
So increase the number of windings. Okay. Second, something else. What for just a simple coil? What influences the self-inductance also? The number of windings. The kernel inside. So what is influenced? Which constant? Or it's basic electrical engineering from the first semester. It's mu. How is it called? You know? Starts with the P. Yes.
German and
Yeah, in English also. German journalism. Differently pronounced. So mu r should be as huge as possible. Under which condition? What kind of material produces the huge mu r?
that will be then close.
Exactly. So if we use ferromagnetic ones, then L22 becomes L1. If you think of transformers in real world, of what material they are built of? Usually, if you go to Thomas Lightly, ferromagnetics. So usually some sort of metal. They are heavy. If you produce studio transformers. So, this does not apply for transformers Thomas Quick uses. So never go to Thomas Quick. Because there they have not so much windings. They do not use ferromagnetic material very often, but just other material size we put the UR plus 1. Then it's not an ideal transformer. Just want to say. So if you want to live on the good side of the world, where everything is quite easy, in terms of transformers, we do not measure the world of transformers. I don't want to say that, but then please, well, we stay there. So if we can say under the condition that L11, L22 is very huge, and then we have I2 is approximately equal to 1 over alpha times I1. And that's what we know from school, right? But you're electrical engineers, and you know, yeah, be careful, it is not always an either transform. So now I want to give you other examples. So this is a very simple example for an electrical domain where you couple one side of an electrical domain and another side of an electrical domain. I want to give you a second transformer which transforms electrical energy into mechanical energy, and we know this, it's a motor drive, and it's depicted here. In its simplest form, when you learn electrical drive first time, you know, the torque produced by the electrical drive is given by some constant times the current through the anchor winding, and we get the torque. And on the other hand, you know that always just the drive is rotating, you get some induced voltage, and very often it's given in that form. So you have this very same relations. A DC drive is in here. A DC drive behaves like a transformer. That's interesting. So, but it couples two different domains in its most general form. Now I give you I want to give you a last one. Think of the mechanical transformer, which transforms just in an electrical domain. You know this already, I think. You use it every day, I think. Mechanical transformer, which transforms from mechanical to mechanical, but changes something, and we have to discuss what it's changed from. The gear, right? If you are bicycling, you're using gears. What is transformed? Torque into torque, and velocity, so angular velocity into angular velocity. And the working principle is always the same. It's this one. So flow corresponds to torque. Torque is corresponding to torque by means of a proportional factor, what we know, based on the size of the meter. And the angular velocity is reciprocally combined. And if you, and this is something you can do at home, if you multiply Q1 times F1 and you multiply to your C, that's equal to E times A2 times F2, because it's power preserved. So the working principle is the same. Are gears operating according to this simple idealized world? In real world. So if you take a bicycle with a gear in it, you is it operating according to this principle? There's scripture. Well, is there somebody doing mechanical engineering in some sense? So mechatronic engineers here in the room? Somebody? Nobody? Okay, then let's talk about the transformer in the electrical domain. Then everybody's with me, hopefully. Well, take an electrical transformer. Do you have some sort of dissipative elements? Yes, this coil. Yeah, the heating of from the coil. What do you do with the heating of the coils? You don't coil. Yes, you can cool it down, but if you want to, we're just thinking in models. What do you do if you want to model this? The coil heating. Exactly. So if you think of a transformer I was represented in the basic electrical engineering lectures. So what you get, the point heating, the dissipative element is represented usually on one side of the transformer. You get a resistor included. If you ask a mechanical engineer for real world gears, he would say, yes, I associate on the primary side of the gear the friction element. But what I want to mention is, or want to point out, you are able to completely separate the dissipative phenomena from the working principle of the gear. Right? Now let's go on. Is the gear storage free, the real gear?
I think it will have inertia still.
Exactly. So you have inertia because the wheels of the gear usually are built of some material which has a certain mass. So if it's massless, massless gears, wonderful. That's something for bicycles we want to have, right? So, but usually they are not massless, so you have inertia, and this inertia can be represented. Inertia in this case is mechanical engineering, in our case, a capacitor. Well, this kind of storage element can be associated to one of the sides of the working principle of transforming the problem because, well, it's just stored, rotates, and it drives the gear on and on for a certain while until the storage is empty. So, as you see, you can completely separate the storage phenomenon from the working principle. So, and let's last example, if you take the electrical transformer, you also have storage elements. What kind of storage elements do you have there? Capacitors, yes, no, but something else. Yes, it's the inductors. The inductance, right? And usually, if you draw the equivalent circuit of a so-called transformer, you build this transformer by means of simpler elements, so basically inductance, self-inductances, and so on. And at the very end, you end up with a equivalent circuit. If you ask the electrical engineer, ETI, if you ask them, they leave at the very end, they just draw the side effects from my perspective, and leave the transformer working principle out and their pictures sometimes. So that's perhaps interesting. So the question appears, what is a gyrator? If we now understand the transformer, what is a gyrator? It's given here. Well, the working principle is again described by a governing equation. So in this case, we have a relation between efforts and flows, and reciprocally flows and efforts. So effort 1 corresponds to flow 2 times V, the beta, sorry, and flow 1 corresponds to effort 2 times 1 over beta. So you have a transformation of the working. Well, the working principle is efforts are transformed into flows, and flows are transformed into efforts. You might say, hey, is this existing? Such an element? The interesting answer is yes, of course, it exists. And I give you one example, which is given here, a hydraulic mechanical transducer, which is called a gyrator, or is a gyrator. Why? Suppose you have a transducer where a volume flow enters the chamber on the left-hand side and pushes the piston to the left, to the right. So what happens if it's idealized? Again, no dissipative elements, no massless, so everything we would like to have. What happens? Of course, the velocity of the movement of the piston must be equal to the velocity of the hydraulic current. Everything is transformed completely into the velocity of this area here.
So we can say the velocity on the mechanical side is equal to a 1 over alpha, a 1 over a, which is the square area of this area here, times the volume flow, because the volume flow divided by the area gives the velocity, so we know the velocity of the piston. Now what happens with the force, it's obviously the same. If we have the pressure here, pressure times the square area is the pressure here gives obviously the force. And in our case, force corresponds to A times pressure. And now we have the relation. Pressure relates force equals to flow, or is equivalent to a flow variable. And here we have the velocity, it corresponds to the effort variable. And on the right hand side, we have the flow variable. Now we'll see the derivation. So we have a transducing principle which interchanges the variables, which is sometimes from the my perspective interesting, but it's a completely different argument. What I wanted to highlight here at the very end. Now let's have a look at what happens if you define your effort and flow variables differently. For example, you say, okay, for me, my intuition says force is more easy to understand being a effort variable, and velocity more being understood as a flow variable. What happens? Well, this hydraulic movement element, what I depicted here, becomes a transformer, right? And if we do the very same for the electrical engineering part, and in mechanics, then the DC drive becomes a gyrator. So be careful if you're doing, for example, on Bell-Salzburg, we define it differently than we do. DC drives are gyrators, and these things are transformers. But now we know what we do. If you want to change the variables just mathematically, what you have to do is to introduce a gyrator with better equal to 1, because then you have an interchange of the variables. That's it. So obviously, this is very important for one of the later chapters. So huge remark at that point. You can always interchange the effort and flow variables by introducing a gyrator in between with beta equal to 1. Then you get efforts to flows and flows to efforts. It's always the same. So obviously, if we can do this, strange idea, we can always transform something like a capacitor into a vector and then vector into a capacitor. Something interesting we should understand later on. So, but at that point, we know we have these types of coupling elements, gyrators, transformers, etc. And yeah, that's it for today. And the interesting part is the watch, which is calculating under which condition the air conditioning here in the lecture hall is cut off. It's a different one than this one. So have a good time. Bye-bye.